Hello, welcome to all. In this episode, we are continuing with the discussion application of Schrodinger equation to hydrogen atom. So some results we have already discussed, how the equation is set, the Schrodinger equation is set, and how it can be solved, and some of the results also we have seen. Now we are going to discuss or interpret some more results in this episode. So that is what we are going to do. Okay. So when we solve this Schrodinger equation, after converting the Schrodinger equation to polar spherical coordinates, quantization arises, quantum numbers come, certain numbers come there, and only when you assume certain values to these numbers, the Schrodinger equation, the conditions of the Schrodinger equation will be set. It can be solved only in that way, right? Three quantum numbers arises by Schrodinger's approach or by solving Schrodinger equations. They are given the symbol N, L and ML that you already know. The quantum numbers provide information about spatial distribution of an electron. So that is the information given by the electron, how this electron is situated or how it is distributed in the atom. That is our concern. Especially electron can be found in some place or other place. So this place, or especially how an electron is distributed, can be expressed in terms of quantum numbers. That is our convenience. So we have three quantum numbers arising from Schrodinger equation. The first one is, of course, principal quantum number. That is quite similar to the quantum number, Bohr quantum number. In the Bohr model, we have seen the quantum number n. So the values are the same. It starts from 1, 2, 3, etc. It can go like that. And this quantum number indicates something. It indicates the energy of the electron. As we have already seen in Bohr model, quantum number quantizes energy. So that role is played by principal quantum number here also. And also it gives an idea about the average distance of the electron from the nucleus. So when the quantum number increases, its average distance of that electron from the nucleus also increases. That is it. And we already have seen in Bohr model, energy also increases. Here, that is true. So all wave functions which have the same value of n, we say it forms a shell. So principal shell. Atoms, electrons are arranged in different shells, we assume. K shell, L shell, M shell, etc. So K shell means the first energy level, first main level we say, and n equals 1, then n is equal to L shell, and so on. That's it. And in the case of hydrogen and hydrogen-like atoms, energy of the electron is determined by this quantum number alone. So we have this expression. This expression we have already seen, 2 pi square mu e raised to 4 k square by n square h square. K is what we call 1 by 4 pi epsilon 0. When value is put into equation, you get the second expression. That's all. And here we can see that if the atom is fixed, the nuclear charge is fixed, everything is okay, then only variable will be n. So energy is quantized by this equation. So this is true for our quantum mechanical model or Schrodinger equation. When we apply Schrodinger equation to hydrogen atom also, we can see that energy depends on n alone, the principal quantum number alone. We have other quantum numbers also, but energy is determined by n alone. That is true for hydrogen and hydrogen-like atoms. But when you go to multi-electron atoms, it's not like that. Because in such cases, we have the electron-electron interaction also coming into play, and there the spatial distribution of electron will have a role in determining electron-electron distribution. And when the spatial distribution changes, what happens? The energy value also will be different. So in the main level, we say there are sub-levels. So we are going into that now. This is the second quantum number, azimuthal quantum number. So this actually stands for the quantization of angular momentum of an electron. We will come to the expression for angular momentum a little later. But As energy is quantized, angular momentum is also quantized, and the quantization equation here and the quantization conditions are different from Bohr model. So that is an important difference. We will be coming to the equation a little later. Now we just go through the quantum numbers. And L value can start from 0 and it can go up to n minus 1. That is also whole number value is possible for it. So L is equal to 0 to n minus 1, 1 to 3, etc. So number of L values that give us what we call subshells or sublevels in the atom. The allowed values will depend on value of its range from n0 to n minus 1. That is it. Okay, the next quantum number is what we call the magnetic quantum number. Sometimes it is simply put as M, but the proper notation is ML. It actually describes the orientation of the region of space occupied by an electron. Electron occupies a region of space, how it is oriented in space with respect to an external magnetic field. That is of importance. So we can identify this orientation only with respect to a reference, and that reference is an external magnetic field applied, because electron movement, orbital movement will have an magnetic effect, and this magnetic moment of the electron, orbital magnetic moment of the electron, will get oriented because of the influence of external field. Then we consider the orientation of this region of space where the electron is found. That is it. The allowed values minus L2 plus L through 0. So that much number of different orientations are possible, that we say. Right, now we can have a picture of number of orbitals. Each orientation refers to what you call an orbital. N, L and M are specified. We say we have an orbital. N is the main level, L is the what we can call it a sub-level or so, and if you fix M also, we say it is an orbital. Right, orbital actually refers to the wave function of specified N, L and M. We call it as a spatial orbital because it is specifying the spatial orientation as well. That is it. That's the quantum mechanical approach. Usually in your higher secondary classes, you may have studied as orbital is the space where there is maximum probability of finding an electron. It's not actually referring to the space. So that is a physical definition, but the actual definition or actual approach is that we take the wave function. Wave function, if you fix N, L and M, so you have a particular wave function from Schrodinger equation, which solves Schrodinger equation, right? And that particular wave function is referred to as an orbital. That's called a spatial orbital, right? In that way, you take the different, you may have already gone through these things in the higher secondary portions, but it is quite simple. N is equal to 1, you have only one sublevel, 1s, because L and ML will be 0. It has only one orbital. N is equal to 2, you have S and P, 2s and 2p. P level, there are 3 orbitals because ML can have 3 values, minus 1, 0, plus 1, and so on. So you have D, 5 orbitals, 3D, 5 orbitals, 4D also 5 orbitals, 4F, there will be 7 orbitals that you have already seen in the higher secondary classes. So I am not going into the detailed discussion of that now. So each ML value represents an orbital of a particular spatial orientation. That is it. Spatial orientation has significance when we apply an external field. That is our reference. That's all. Okay. Now we have already seen the solution and wave function. Now you take the radial part, radial wave function we say, because we are taking into consideration the radial part because the angular part we know for s orbital the angular part is a constant, so there is no problem. If you take the total wave function or radial part, it is almost similar. So it's the radial function multiplied by a constant gives the total wave function there. That's fine. But for other orbitals, you have the radial part and angular part. So we are considering a radial part. What is the radial part? The part of the wave function that is notated by r, which depends on distance from the nucleus alone. So we are considering the variation of the wave function when we move away from the nucleus here, whatever may be the orbital. Right, here three orbitals are considered. First, you go to the 1s orbital. You can see that wave function has the highest value when r is equal to 0. Wave function has maximum value at the center of the nucleus. That point you usually misses, but that is it. For 1s orbital, it has a maximum value at the center. And then what happens? It exponentially decreases like that. When r tends to infinity, it goes to 0. That is it. Then you come to 2s orbital. There also you can see that the value is high, close to the nucleus. Then what happens? It decreases, it reaches 0. Then wave function go to the negative value. Then it again asymptotically approaches 0 as the distance approaches infinity. That is it. So you can see that wave function has two regions in the case of 2s orbitals. In one region you have positive value, and in one region you have negative value. And the positive value decreases, continuously changes, reaches 0, and then becomes negative. That is it. So there is a point between these two regions where the size or wave function is equal to 0. Here we are put it as r, it doesn't matter. And that is what we call a node. So at a node, you have two sides. One side the wave function is positive, the other side the wave function is negative. That is it. Here it is a radial function we are considering. So this is called a radial node. So it will be spherical as well. The node will be spherical because you are not specifying the direction here. You are considering the distance alone. So the node is spherical. So there will be a spherical surface where wave function becomes equal to 0. That is what we call a radial node. In 2s orbital, we have one radial node. Okay. Some more orbitals are given here. 2s, we can 1s and 2s we have seen. And 2p, there is no node as such. It's different. 2p, the xi value is initially 0 near the nucleus. So that is it. In s orbital, whether it is 1s or 2s, you can see that the wave function is highest towards the nucleus. But here it is 0. So you can have wave function of s orbital inside the nucleus as well, but not for p orbital. That is it. It increases and then decreases, as you can see. Right, 3s, you can see that for 3s, towards the nucleus it is high, it decreases, reaches 0, becomes negative, and then again increases, and again becomes 0, and then you have a positive value, and then finally asymptotically reaches 0 towards infinity. So what does it indicate? So first positive region and negative region, there is a point where that point is a spherical surface actually. A spherical surface where the wave function becomes 0. Similarly, there is another point also where the wave function converts from negative to positive value. There also it becomes 0. So in 3s orbital we have two nodes. That is it. 3p is similar to our 2s, not exactly similar, but somewhat look like 2s, and it has one node. 3d, there is no node. That is it. Now we are considering the square of the wave function, right? It should be exactly psi star or r star. Here we have put it as r square, right? Square represents what you call probability, right? So you can see that 1s orbital probability is high, probability density actually, not probability, but probability density. Probability density is maximum at the center of the nucleus actually. That point you should not miss. Probability density is high inside the nucleus. Then it decreases like that. That is it. So as you move away from the nucleus, exponentially the probability of finding the electron decreases. Close to the nucleus we have more probability density, that is it. 2s orbital, you can see that it decreases from the nucleus, reaches 0 and then increases, right? 2p, it is 0 in near the nucleus, it increases then decreases, you will have. So in 2s orbital you have a knot. 1s there is no knot, 2p also there is no knot. Here we have to come across what we call radial probability function. The radial probability density we have already seen, that is I square or r square. Radial probability function, it is defined in a particular way. You consider a spherical shape around the nucleus. You consider a spherical shell of very small thickness dr, the differential thickness dr. And we are considering the total probability of finding the electron within that spherical shell. That's important. So you have dr thickness and r at the distance r. So we can consider such concentric spherical shells, large number of spherical shells, and we are considering the probability in those spherical shells, just starting from the nucleus, right? You take the nucleus. If you put r is equal to 0, then this is given as 4 pi r square psi square for s orbitals. It is taken as, because there is no angular distribution there. You have to consider the whole area. So it will be put like that. And because of that thing, if you put r is equal to 0, this function becomes equal to 0. So what does it mean? At the center of the nucleus, you will have no electron. That is it. And if you consider a very small space inside, the nucleus is very, very, very tiny. Then you do the integration using this expression 4 pi r square psi square, and you take the size of the nucleus, that is too small, the probability will be small. That is it, right? Now we come to the curves there. We have 4 pi r square psi square or r square r, for this is for what you call the p orbitals and d orbitals. And because when you change the direction, their probability changes, hence we are considering a particular direction only in such cases. That's why we put it as r square r. That is it. Okay, what happens to this probability for 1s orbital? It is 0 at center of the nucleus, it increases, reaches a maximum and then decreases. N is equal to 1, L is equal to 0, 1s orbital is like that. So you have the point corresponding to the peak of the curve. So that will be the spherical shell having the maximum probability, right? And that is the what we call the radius of hydrogen atom. Sometimes we take it as, consider it as, and if we can call it as the most probable distance of the electron from the nucleus, and this corresponds to our Bohr radius itself. This corresponds to A0 itself. That is it. When you come to 2s, you can see that a smaller peak initially, then a larger peak, right? So you have two regions of high electron density. We can see there is, so we can say that 2s electron penetrates close to the nucleus because of that small lobe there, and in between you have a place where you have 0. We say we have one knot. When you go to 3s, we have 2 knots. 2p, you have no knot. The curve is similar to that of 1s. 3p, the curve is similar to that of 2s. 3d, the curve is similar to that of 1s. Which curve? Radial distribution function. That is an integrated value, right? We have to do the integration over that, then only you get such things. Okay, that is it. Now we come to what you call angular distribution or shapes. When you consider the angular distribution also, we see that in orbitals we have certain angles give you larger probability of finding the electrons, and we call it as angular distribution. And this is not a graphical representation, but this is what you call a contour map. What is a contour map? We identify a region where probability is high and we draw a line of identical probability, and this encompasses highest electron density, or it envelops a region within which the 90% probability of finding the electron will be there. That is it. That we call as shape of the orbitals. These are the shape of p and d orbitals. We know p orbitals we consider as projected towards the three axes, x, y, and z axis. It has two lobes each, and we have the px orbital. Then yz plane bisecting it will be a nodal plane. We sometimes call it as angular node as well, where the probability is 0. You can see that this wave function will have positive value in one lobe and negative value in the other lobe. But if you take the probability, it is squared. That is it. So this is not an orbit in the sense of Bohr model. This is not an exact path of the electron. It surrounds the space or area where we have the maximum probability of locating the electron. That is it. Usually a 90% probability will be located within that. That is it. Then d level, we have 5 orbitals, you know, and d orbitals will have 2 angular nodes. dxy, dxz, dyz, they project in, they have 4 lobes and they project in between the concerned axis. X square minus y square project along the x-axis and y-axis. Z square has special shape that you know, 2 lobes and a ring of electron density. And all of them have 2 angular nodes each. Now we come to the concept of node. Node we have already explained node. So radial node is a spherical surface where the probability of finding electron is 0. That I have already explained. Angular node is also called a nodal plane. Angular node is a plane that passes through the nucleus. That is the case everywhere. And we can have the number of nodes. It depends on the quantum numbers, number of nodes. Number of angular nodes is equal to the azimuthal quantum number or angular momentum quantum number, L. So L is equal to 0, there is no node. S orbital has no angular node, right? L is equal to, okay, L is equal to 1, there is 1 angular node. P orbital has 1 angular node. L is equal to 2, we have 2 angular nodes, d orbitals, and hence f orbitals will have 3 angular nodes, and so on. And number of radial nodes can be given by the expression n minus L minus 1. That is it. So you take 1s orbital, 1 minus 0 minus 1, it is 0. There is no radial node in 1s orbital. If we come to 2s orbital, it is 2 minus 0 minus 1, there is 1 radial node. 2p, 2 minus 1, 0, no radial node. 3s you have 2 radial nodes. 3p you will have 1 radial node using this formula. 3d you will have no radial node. You can come to 4s, 4p, 4d also in similar manner. 4s there will be 3 radial nodes. 4p there will be 2 radial nodes. 4d there will be 1 radial node. That is it. Now we come to the angular momentum of electron. I have already stated that angular momentum is also quantized. So it is quantized according to Bohr model also. But the expression in Bohr model, we have seen it as nh by 2 pi, angular momentum equation is given by. But in quantum mechanical model or Schrodinger equation, when you apply Schrodinger equation, we see that angular momentum depends on the azimuthal quantum number or angular momentum quantum number, that is L. And of course, this will be a vector quantity. So we represent it as a vector, and it is equal to square root of L into L plus 1 into h by 2 pi or h cross. That is it. So we can see that we have s orbital of any main shell. It doesn't matter. L is 0. So s orbital, in s orbital, electron has no angular momentum. 0 angular momentum. P orbital, it will be 1 into 2. That is square root of 2 into h by 2 pi. D orbital, it will be square root of 6 h by 2 pi. Similarly, f orbital, it will be square root of 12 into h by 2 pi. That is it. Angular momentum projection of quantum number m is associated with azimuthal angle and is related to z component of angular momentum of an electron in a hydrogen atom. Right, we have a reference axis. That is, the z axis is our reference axis. We are applying an external magnetic field. Suppose you are applying an external magnetic field. Then what happens is that this angular momentum of the electron interacts with the magnetic field. The angular momentum of the electron produces an orbital magnetic moment that interacts with the external magnetic field, and this get oriented. The magnetic moment of electrons get oriented. It will have certain orientation. So there will be a corresponding angular momentum of these orbitals as well. And we consider the projection of this angular momentum of the electrons towards the reference axis, that is the z axis. Right? That projection is given as Lz equals L cos theta. That is it. Theta is the angle you make with the z axis. Right? And that we call it as azimuth angle. So you can consider it like this. The vector is represented as L vector here, and its z component. The angle that vector make with z axis is theta, and the z component of it is represented as Lz, and that will be equal to L cos theta, where theta is the angle made by the angular momentum vector of the electron with the z axis, that is our reference axis. That is it. And this magnetic quantum number ml, actually its significance is that Lz will be equal to m into h by 2 pi. So we have the m values there, which range from minus L to plus L. That is it. Minus L means it is in the opposite direction of the externally applied magnetic field. That's all. Or in the opposite direction of the vector will be exactly in opposite direction of the positive side of the z axis. That is the significance of that. So it is plus L, that means it is exactly aligned with the plus z axis of it. For any other direction, you will have this type of a z component, and that z component cannot have any desired value. Its value is limited by this magnetic quantum number. That is the significance of magnetic quantum number. So any possible orientation at any desired angle is not possible. Only certain angles will be possible with the reference field. Reference field is the externally applied field. That is it. So these are the what you call the magnetic moment, angular momentum of the electron in different orbitals. It goes on like that. SPDF, GH, we notate the orbitals. This arises actually from what we call spectroscopic terms: sharp, principal, diffuse, fundamental, etc. These are the names given for different spectral lines arising from these electrons in these levels. Right, s orbital, s electron, due to its transition, usually get sharp lines in the spectrum. P electrons give the principal, that means it will be of higher intensity. It may not be very sharp. Sharp means a particular frequency, very exactly. So principal means more intensity, but that frequency may be a small range, very small range. Diffuse means the frequency is of a larger range. That is it. Now, what is an orbital? The definition for an orbital is the wave function based on these three quantum numbers is called orbital. So our psi is what you call orbital or orbital wave function. So orbital is a short-term method to say an orbital wave function. That is all. Probability contours are often referred to as orbital as well. That I have already discussed. So we have the contour map within which we have the highest region of probability. That is it. That is sometimes referred to as orbital. But the exact definition is the wave function itself is known as orbital. Yes, these are the shape of d orbitals. Now we come to the other quantum number, the fourth quantum number, that is the spin quantum number. Right? Spin quantum number is indicating the orientation of intrinsic angular momentum of an electron in an atom. So electrons are what you call fermions that obey a particular set of rules put forward by Fermi and Dirac. We need not go into such details. Such particles have what you call an intrinsic angular momentum, and that is quite similar to the effect produced by spinning of a particle in classical sense in Newtonian mechanics. In quantum mechanics, it is not a physical spinning, but it is a different phenomena in which it has a spin, it has a half integral spin, we say. Such particles are what you call fermions. They have what you call half integral spin. And it can be compared with the rotation of a particle, rotation of Earth around its own axis. Similarly, electron also can be considered to be rotating like that in a classical sense, but actually the case is not so. The particle is having some property. It's concerned with certain other things like symmetry of the particle, symmetry of its wave function, etc. Okay, we need not go into such fundamental details here. But we have to see that matter is made up of such particles. Electrons, protons, etc. have what we call half integral spin. So spin of an electron is 1/2. That is it. Its angular momentum, intrinsic angular momentum of an electron will be half h cross or half into h by 2 pi. It's a vector-like quantity and is quantized spin quantum number. Okay, this is given as the angular momentum is given as, I have added a little, the spin quantum number is half and angular momentum value is given as square root of s into s plus 1 into h cross. That is it. That arises from quantum mechanics, not as simply as s into h cross, but it is s into square root of s into s plus 1 into h cross. That is it. That you give the angular momentum. So if it is you have a single electron, its spin quantum number is half, then it will be half into 1.5 h cross. So it will be 3/4 square root of 3/4 h cross. Half into 1.5 and you take the square root. So it will be square root of 3/4 into h cross. That will be the angular momentum of a single electron. Okay, now this, when you apply an external field, the spin of an electron, it is compared to the physical picture here. Spin of an electron can orient itself in two different ways. One is called the upspin and one is called the downspin. So upspin simply means it aligns with the applied field. Downspin means it opposes the applied field. A magnetic moment is created by the spin of the electron, what we call spin of the electron, and that magnetic moment, if it aligns with the applied field, it is upspin. If it opposes the applied field, it is downspin. Right? That is it. So it can align only two different ways with an applied field. That also arises. This arises actually from Stern-Gerlach experiment. where we have what you call the one spectral line splitting into more than one line, and there are some other experiments also in which this spin of the electron is proven. So spin of the electron can orient itself to an applied field only in two different methods, two different ways. So magnetic moment of the electron align with the applied field or it opposes. When it is aligned, we have what we call up spin, and when it is opposing, we have down spin. Up spin is indicated as plus half and down spin is indicated as minus half. That is it. Actually, the quantum number we should represent as ms. Ms can have two value, plus half or minus half. S represent what you call the value of a particular electron, or you add, if you have a number of electron, you have to add all the plus and minus half, then the total number can be taken as S. S is the total spin, right? You have, suppose you have 5 electrons, 2 of them are paired and one is unpaired. Pair means plus half and minus half, they will cancel, so only one is remaining. That is it. So, or you have 3 electrons in the p level, you have px, py and pz, right? All of them have parallel spin, all of them are having up spin, then the total spin will be plus half and plus half, that will be 1.5. Then the angular momentum is have to be calculated according to this equation. S value has to be put as equal to 1.5 there. So 1.5 into 2.5. Then you take the square root. That is it. Right. So that will do with our discussion. So this much is required for us in the discussion of hydrogen atom. So we have almost gone through the application of Schrodinger equation for hydrogen atom. Then what is remaining in quantum mechanics is a simple discussion how a bonding take place or not. That we can defer it for the discussion of chemical bonding coming soon. That is it. Thank you all. So you can easily go through this lesson. You can refer to the PDF already given, and now you are ready to answer questions based on the application of Schrodinger equation for hydrogen atom and hydrogen-like atoms. Thank you. Bye. See you.